Sure. So I'm an NVIDIA and I work for NVIDIA. I'm a solution architect and I specialize in neural network development. So over the last, I would say, 10 years or so, I've been helping various organizations. Those are academic organizations, but also commercial organizations build and deploy large neural networks. And today I'll be talking specifically about that. I'll be talking about large neural networks, why do they matter, and how they are transforming several different fields of artificial intelligence, and in particular, natural language processing.
Okay, sounds interesting. We already had two great sessions yesterday with your colleagues Manuvir and with Eric.
Yeah.
So we're,
Amazing.
You're the third NVIDIA employee here in the event. So we're looking forward to hear more about what you have to say. So take it away. If you share your screen with us, we can.
No problem. Here we go. I'll share my audio as well because I have some recordings. Let's see how they work in this format. So here we go. Hopefully everyone can see
everything comes out clear.
I'm trying to show. So yeah, my name is Adam. I've already done the introductions, and today we're going to talk about large neural networks. And I think it's a very important topic to discuss because, as you might or might not be aware, over the last decade, the size of a typical artificial intelligence model that we are using has been growing quite dramatically, in fact. So this is just a random selection of key natural language processing algorithms spanning the last 4 years. And if you notice here, the y-axis, that is not a linear axis. So every time we make a step increase on this plot, that means that we are increasing model sizes by an order of magnitude. So in just the last 4 years, the size of a typical model for natural language processing increased by 1, 2, 3, 4 orders of magnitude, almost 1000x. And it's important to step back and ask a question of why? Why is that the case? And should we, as a humankind, continue to build even larger models? And this is a very important question to ask because, as some of you might know, with larger models comes improvement in model performance. So for those of you that haven't heard, neural networks are governed by scaling clause, meaning that their improvement is very predictable. Every time we increase the amount of data that we use for training, every time we make them bigger, they improve by a fairly predictable amount. And this graph shows that for natural language processing. But I think there is a fundamental question to be asked here. Is it worth it? Is this incremental improvement in test loss, in this case, this is a natural language problem, so I think this reflects perplexity of the model. Is it worth the 10,000x speed up that is required to build those architectures? And if the only thing that we would be achieving would be this small incremental improvement to perplexity, small incremental improvement to the test loss, the answer would be definitely not. So we should step back and ask ourselves a question of, is it really the only thing that we have achieved by building larger neural networks and training them with substantially more data? And unfortunately for us as a community, the answer is no. So those models not only provide us with as I mentioned already, small incremental improvement in accuracy, but they have some fascinating properties that make them more than worth a while, and that are a reason why they are very likely going to displace all of the other smaller neural network and other architectures, in fact. So today I'll focus on 2 of those properties. First of all, larger models counterintuitively are cheaper to train. And that might seem odd, but if you look at how they behave, it turns out that large language models are substantially more sample efficient, meaning that with a smaller numbers of iteration over the data, they achieve better performance faster. So what you're seeing here are 4 largely identical neural networks built for natural language processing task again. And the green line is the 8.3 billion parameter architecture, and the blue line is 345 million parameter architecture, roughly similar in size to Bert Large. And what this graph shows you is that not only the smaller architectures achieve substantially smaller performance overall, but even to achieve this target performance, they have to do quite a few iterations over the data. Whereas the larger architectures, even after a single epoch, single iteration over the training data, can achieve not only very good performance, but also performance that in this particular case exceeds the capability of those smaller models overall. And in fact, this is not just a coincidence. It turns out that there are some very predictable mechanisms that govern this behavior. And it turns out that for any given computational budget, there exists an optimal model size and dataset size that will lead to the maximum performance. And as of today, with the current state of knowledge that the humankind has, there is no escaping that. So what this graph on the right shows is that if you have, given computational budget, there exists an optimal model size. And if you choose a smaller model, you will get substantially lower performance. And if you choose a larger model, you will have to pay unproportionally more in terms of the computational cost. So choosing smaller architectures, for example, for natural language processing, choosing Bert Large, which is a tiny architecture in comparison to some of the models that we have at our disposal, is very rarely a good idea for most of the problems. But more interestingly, when we look beyond just traditional use of natural language processing models as like feature extractors, large language models and more broadly, large neural networks are also few-shot learners. And this is a very important property that makes them extremely appealing for the future of natural language processing, but more broadly, artificial intelligence. For those of you that haven't heard of this term before, a quick recap and then a demo to demonstrate what I mean by that. Effectively, what you're seeing on this plot are three largely identical neural networks. They predominantly differ in terms of their size. So the green line represents the smallest of models, which contains 1.3 billion parameters. The orange line, 13 billion parameter model, and the blue line, 175 billion parameter model. All of those models were pre-trained on very large textual data set. And then all of those models are being adapted to carry out a new task, a task that they have never seen before. And as you can see, the smallest of models, when exposed to relatively small amounts of data, so this indicates a single sample, this indicates 10 samples, and this point indicates 100 samples, they are unable to adapt to a new problem. So for those smaller architectures to be able to be adapted to new natural language processing, but in fact other tasks as well, you need to really master for every single task a relatively sizable fine-tuning dataset. Whereas as those models grow, they gain the capability to adapt to new problems dramatically faster. So as you can see, the largest of architectures listed here, despite the fact that it was in this case exposed to just a single training sample, will exceed the capability of both of those models, despite the fact that they were fine-tuned on 100 samples. So this is the few-shot learning capability of those models. They learn how to conduct new things exceptionally quick, and even in zero-shot setting, where you don't give them any examples whatsoever, but simply ask them to carry out new tasks, they perform relatively well. So if that doesn't make sense, don't worry. Let me show you a quick example of what I mean. So let's look at three different problems. A problem of translation. So we'll in front of your eyes, we'll teach this neural network to translate named entity recognition and chatbot-like question answering type of an application. So So let's give it a go. So what you're seeing in front of you right now is a very simple interface over a very simple GPT neural network. That neural network is only capable of doing one thing and one thing only, namely, if you, that's annoying. If you, okay, that's really annoying. I will have to deal with it. And let's not worry about it too much. Okay, if you type into that neural network some text, if you provide that neural network with some text, the only thing that it is capable of doing is generating further text. That is the only thing it was trained to do. So if you provide into that neural network some random input, like in this case, test text, it will generate fairly random output. But let's teach it something. Let's teach it to do something meaningful. In our case, and I'm terribly sorry, this was supposed to be a video, but my Outlook decided not to, PowerPoint decided not to collaborate with me. So, but if you provide it with some training samples, in this case, 1, 2, 3 examples of how to translate from English to French, by literally just providing it with a statement English, I do not speak French, and then the appropriate translation, we can encourage it, we can train it effectively to translate. So when in the 4th segment of text, we ask it, what rooms do you have available? It has then the capacity to generate an answer, and an answer that is in most cases relatively good. So with an approach like this, and obviously with just free training samples, you will not achieve state-of-the-art of English to French translation, but it's nevertheless fascinating that with just free training examples, we could achieve something as complicated as teaching this neural network to translate. But that's not the end of the story. So if we don't change anything, we just stick to this user interface, and instead, and this is an example where I'm showing that it actually translates reasonably well. If we instead provide it with a piece of text describing some fruits and their flavors, and then provide just a single example of how to do named entity recognition. In fact, so what it means is a single example of how to find names of fruits, their colors and flavors in this text, we can reasonably expect it to learn how to do named entity recognition. And in fact, I'm submitting the request here and getting a response. And in fact, it correctly finds the names of the fruits, their colors, so grayish blue, and their flavor tart. And those are deliberately abstract names of fruits to make sure that we're testing its named entity recognition capability and not its capability to memorize fruit names, which it would totally do if we gave it an opportunity. So, and in the 3rd example, I'm teaching it how to become a chatbot. Again, in exactly the same way, I'm just providing it with a description of what I would like it to do. Maya is a chatbot that talks to 5th graders about astronomy. She answers using a language a 5th grader would understand. And then I'm providing it with 3 examples of what does it mean to be a chatbot. So student, what is the difference between a meteor and meteorite? Myra, a meteor is a small rocky object in space. And then a 2nd example. Following that, a 3rd example, does Pluto have a moon? And at the end of that segment with 3 examples, I'm actually asking the neural network a question of how far is Mars from Earth, and and we get an answer. And we get an answer that is not necessarily factually correct, but it's very sensible. But mind, this is just 3 training examples. So roughly 225 million miles from Earth, as the planets in the solar system all orbit the sun, our distance to other planets changes every day. So that is remarkable that with just 3 examples, we've managed to train this neural network to translate, carry out named entity recognition, and effectively provide a question answering chatbot like functionality. So what I showed you, that's kind of the core definition of few-shot learning, but this is in fact just a toy Using an approach like the one that I've showed you so far will not allow you to achieve state-of-the-art performance. And if you compare the blue line, which indicates the performance of prompt design methods to more traditional methods, you'll see that there is a fairly sizable gap between them. So they work, but they don't work perfectly. But with just small adaptations to the approach, we get results that are on par with state-of-the-art, despite the fact that we need only a small fraction of the training data. And by those approaches, I mean prompt tuning, p-tuning, and other more modern approaches such as AI-free for parameter efficient fine-tuning. So I have some examples of those. It's annoying. I have few examples of what it practically means for the performance of those models. Let's see whether those examples will actually work, because well, my PowerPoint is playing games today. No, they won't, which is super annoying. I've never seen that before. Okay, that's not cool. 1 second, I do have those videos stored as normal files, so I will have them open in literally 1 second. Here we go. Yeah. So let's see what a properly adapted large language model can do. So what you're going to see is, again, a simple question answering application.
Hi. Hello.
But now done with substantially larger model and done with proper configuration and adaptation. Let's quickly have a look.
Hello, Toy Jensen.
Hi, please ask me anything.
What are the greatest threats of climate change?
The greatest threats of climate change are the effects on human health, food security, water supplies, and the environment.
How do astronomers look for exoplanets?
Most exoplanets are found via the transit method. That was the case for the TRAPPIST-1 planets.
Tell me more about that method.
The transit method is when a planet passes in front of its star. The amount of light blocked tells astronomers the size of the planet. The duration of the transit tells astronomers the orbital period of the planet.
What roles do proteins play in our cells?
Proteins are the building blocks of the body. They are the basic materials from which all living things are made.
So that's just one tangible example, but it's too easy to forget that if you have such a powerful tool whereby you can just ask it to do new things, and it does it, you can build much more than just like question answering chatbot-like applications. Let's look what this notion means for, say, the future of software development. So what you're seeing here is an OpenAI project called Codex, where we just ask the neural network, after obviously a level of adaptation, to generate code rather than a human text. And in this case, we can have a meaningful conversation with this algorithm about the process of creating a computer game. So we're asking it to import an image, we're asking it to make the image small, we're asking the model to crop the image circularly, and it generates the source code to build that functionality. And by the end of this exchange in this demo, the authors will have a fully working computer program that implements a video game where you fly a rocket ship throughout a field of asteroids and you gain points. Despite the fact that they haven't written a single line of code, but instead described the logic to the neural network, they have a game at the end of it. And again, you can iterate over this idea and bring it to new heights. Let me show you one last example of Google robotics research and what it means for the future of day-to-day objects that are surrounding us. Here we go.
We start with a user instruction that says, I spilled my Coke on the table. How would you throw it away and bring me something to clean it up? The robot considers different skills that are available to it and selects the best one according to the secant process described above. It uses the affordance model as well as the language model to score the available options. The algorithm starts by finding a Coke can, which is then followed by picking up the Coke can. Once the robot accomplishes that part of the instruction, the skill is appended to the prompt, and the method continues with the next set of skills. On the right, you can see different skills being considered, and there's
So effectively, this robot was trained to carry out basic tasks such as picking, finding a Coke can, but it was never trained to plan those actions, and all of that is done by largely the same language model that was just politely requested to carry out those actions. So those large models are substantially more than just a small incremental improvement in our natural language processing capability. There are fundamental change in the way we do natural language processing, but they are also a more fundamental change to the way we do artificial intelligence. It seems that we are abandoning the NLP approach that we've found in 2018-19, where we had to take huge amounts of text, pre-train models to do things such as masking, and then fine-tune it on a relatively large amount of supervised data to carry out a specific task. Like this thing seems to be the thing of a past. Instead, we seem to be converging towards a different approach, whereas we train one extremely large language model on a very broad collection of text, including not just day-to-day conversations, but scientific text, general knowledge, literature, source code, and many, many others. And then we just politely ask it to do new things. And this creates a huge plethora of new opportunities. Admittedly, it is computationally intensive because building those models from the get-go is difficult. Those models are in public domain, though. So NVIDIA has published a lot of those very large language models on Hugging Face. If you're interested, do check out them. And we've also have an early access to our 515 billion parameter neural network as well. And to start to wrap up, those large language models allow us to solve the unsolvable, and they seem to be creating foundation for what at some point in the future might become general artificial intelligence, because we no longer need huge amounts of labeled data, and we no longer have to create one dedicated model per task. Instead, we're approaching a point where we will create just one large language model. We'll need only a limited amount of labeled data, and we will be able to use that one generic model to solve an extremely broad range of tasks. And that's the point where I'll leave you with a call to action. There are a lot of languages in the world, and all of them need a robust language model. Most of the research is still done on a very small subset of languages that people use across the globe, and we are always looking for organizations that are open to collaboration with us on development of those other architectures or multilingual architectures. It's an important area of research that comes with a very high reward. Admittedly, it is computationally intensive. So especially if you're planning to build your own language models from scratch, you will need sizable infrastructure. For adapting them with p-tuning, that is not the case. So almost every one of you can go online to Hugging Face, download our even 20 billion parameter models and start p-tuning them today. So what I want to say is you don't need to start with the largest of models. There is an entire cycle you can go through, starting with smaller architectures. Even starting with those more traditional language models is a great place to start learning about natural language processing. How do you get started? Use the materials that are available. We have a range of training courses as part of our Deep Learning Institute platform on natural language processing and related topics, such as building multi-GPU training jobs. Within the context of this talk, I strongly recommend the Model Parallelism Deep Learning Institute course. We'll be running a public workshop in the very near future. Do check out NVIDIA developer blog. It's filled with very useful information and training, example notebooks, example scripts for natural language processing of every size. Check out our GTC on demand portal. You'll find a plethora of information there on how to build those models end to end, step by step. And reach out. We're here to help. We're always open to collaborate with organizations that are willing to push the boundary of what's possible in natural language processing. And we're happy to help you at any part of the pipeline, whether that's with data collection, data pre-processing, or production deployment. With that, I'd like to open for some questions.
Thank you very much, Adam. Very interesting. The future looks bright with all these kinds of big models. That's all the things that they've been able to do, especially the graph you showed for the amount of parameters that they had 3 years ago already compared to what they have right now. But don't want to sound negative, but we also notice that some people start to look at the ecological footprint of those models. Because they need a lot of energy to train those models. How is your viewpoint on that?
So, manufacturing of your jacket also required a huge amount of energy, yes? But it's a very important part of your life. And those models are already solving exceptionally important problems in our day-to-day lives. So I didn't cover it in this talk, but we're using exactly the same models to model the behavior of proteins, antibodies, and human DNA. We're using exactly the same models to model behavior of complex chemical pharmacological molecules. And they're already transforming our day-to-day lives. And NVIDIA is very committed to reduction of energy consumption associated with those models. In fact, if you look at the list of green top 500 computers, so this is a list of supercomputing systems that are sorted by power consumption per unit of compute. All of the top entries on that list are NVIDIA systems. So yes, admittedly, those are challenging, but we're pushing the boundary both on the hardware front as well as the software front to make them as energy effective as possible, and also making sure that we're solving problems worth solving with those models.
Of course. No, okay, thanks. It's an interesting viewpoint, especially because if you look at the industry, they also consume a lot of energy, and in the past they also are getting better in their energy consumption. And of course, in these kinds of projects, it will also be reduced over time because we're getting more insights in how to do things. Huh? Yeah. Okay. Thank you, Adam.
The key thing is to solve problems that are really worth solving.
Exactly. Thank you very much for your interesting session. We hope to hear more from you in other sessions another time. I can only wish you a pleasant rest of your day. And
thank you kindly.
Thank you for joining us.
Thank you so much.
Thank you.
All right.
Have
Bye-bye.
a good day.
Bye-bye.
Bye.
So that was another session for the Global AI Developer Days. We'll be back in 25 minutes approximately for another session. So we'll have a short break, and then we hope to see you back